Welcome to my new calculus channel. My name is John Gabriel. And if you recall, in a previous video, part 29, as you see on your screen here, I discussed proposition 1 of the quadrature of the parabola from the works of Archimedes. And somebody then asked me a question on this in a previous video about equidisection of rectangles. And so, as I showed you in here, there were some interesting facts, and I'm going to now show you that question and how to answer it. So, in part 30, the question was this. The question was right over here. It says, it is easy to cut up a rectangle into two triangles of the same area. As for that matter, it is easy to cut it up into 4, 6, or any even number of triangles of equal area. Is it possible to cut it up into an odd number of triangles, all of the same area? Well, it's not possible if those triangles, it's not possible to do it if there are odd number triangles in such a way without distorting the shape of the triangles. Okay, so what does that mean? Right, let's see very quickly. So if you just have one rectangle like this, as you know, it doesn't matter what rectangle you have, even a parallelogram, always there will be a triangle that is half its area. So in between any two parallel lines on the same base, this area is always the same. It doesn't matter how far it stretches. This area here, the entire area of the rectangle, of the parallelogram, is the same as that area, is the same as that area, and is the same as that area. So it doesn't matter what it is. And obviously, by symmetry, the triangles will be the same area too, okay? Regardless of where you go, right? So now, what does this mean in terms of trying to find a triangle with the same area that can be, reassembled into a rectangle? Well, if it's just a rectangle, you can't do it, right? Because the triangle will be the shaded area. This shaded area has the same area as this triangle. So if it's one, you can't do it. But if it's two, you can, see? Because then it's just this green area and it's equal triangle here, right? Where my cursor is pointing. And so if you have three, the same story, you can't do it because it's an odd number, right? So now, in this video over here, I'm sorry, this one, it's not my video, it's somebody else's. Apparently, he uses something called Thales theorem. You don't have to use Thales theorem, but what Thales theorem says is that if you have three distinct points on a circle and one of the lines joining those points is a diameter, then the triangle must be a right angle triangle. Okay, you don't even need compass construction to prove these facts. So now so you may ask yourself, now, how is it possible to divide any line into a number of equal segments, any equal segments that you like? Well, let me show you a very simple way of doing this without having to know any theory at all. Look, let's say this is the line here, right? And it doesn't matter where you put the line, over there or there or there, right? Let's say that we want to divide this line into two equal segments. Well, isn't it possible if we just had another rectangle right next to it and we had this entire red line, then it's divided into two equal segments, isn't it? It's like saying, how do we represent a half? Okay, so if this is 1, then a half will be this rectangle. But if, for example, this is 1, then this rectangle here will be a half, right? Does that make sense? So you don't really need to, so it's very easy to see that any line can be divided into an equal number of parts by not even dividing that particular line and considering that this red line is just part of a longer line, right? And it doesn't matter how many you have, you can always divide it into, you can always divide a rectangle into an equal number of pieces. And if you can divide a rectangle into an equal number of pieces, each of those pieces has a triangle which represents the area of the rectangle. Okay, so if it's an odd number, you can't take this green triangle and reassemble it into the area without breaking up the shape of the triangle. But if it's even, then no problem. If this is the whole rectangle, then you can divide into 2 triangles, and by equidisection and rearrangement, you can have the same rectangle again. In other words, this area here is the same as the green shaded area. All right? So I hope that answers your question, and it's a very interesting point because you'll be surprised how many think this is simple and straightforward and that it requires compass and straight edge construction. It doesn't. It's like saying, well, if I have parts of a unit, how do I represent them? Well, very easy. Just take that unit and extend it, as I've shown you here. So if you say, for example, wanted to represent half of this line, just take the line, double it up, and then obviously one part of it will be half, right? Similarly, a third part of it will be accomplished by just tripling the line or putting 3 red lines next to each other, as you see here. So does that make sense? Right, and in fact, we can also derive numbers this way. But now a very interesting question pops up. So if you can divide any line segment into an equal number of parts, what if you had a line segment that was approximately, let me just get rid of that, that was approximately 3.14, that was actually pi. Let's say you had a rectangle with the length of pi. Could you divide that into 3 parts? Well, sure you could, geometrically, as I've shown you. If you just add 2 and 3, then this here becomes a third, and this is a third, and this is a third, right? So you've divided into 3 parts. So you can do it that way. But is there a number, if you have to divide a certain line, is there a number that represents the distance of one of those equal parts in the case of pi? Nope, there isn't. Okay, so there is no way, while you can divide any line segment into an equal number of parts, if the assumed line segment is measured according to a certain unit, then there's no way you can measure those parts in the case of an incommensurable magnitude such as pi. All right, because there is nothing that there is no unit that measures pi. Okay, so now I think I've spent enough time on that, and I want to refer you to lecture 4 of the new calculus, where I discuss there are no axioms or postulates in mathematics, and this is very important for you to understand. Now, while the ancient Greeks were unbelievably smart, they did not invent geometry. Did you get that? No. Geometry was around long before the Greeks, or even before the Greek word geometry, okay, which means measure of the earth. Geometry exists even without anything existing because it is based on well-formed or perfect concepts, all right? So the Greeks discovered these facts. They did not invent them. And so you can actually systematically derive every one of the so-called axioms. They're not axioms, they're actually requirements in Euclid's Elements. You can derive them systematically from nothing, from a void universe. And I've created videos which show you how to do that, okay? So for example, the very first one is called the line and the extended line, and there are several in that series. But if you download my new calculus book, which is free, you can read this chapter and find out how it is possible to do this. I was the first to understand this in all of human history, by the way. Nobody before me had a clue that there are no axioms or postulates in mathematics. Well, I hope you've enjoyed this little presentation, part 30, and that you'll join me again next time for a next exciting episode, and where we'll cover more interesting facts. So subscribe to my channel, spread the news, and I'll chat to you again hopefully soon. This is the New Calculus channel, and I'm John Gabriel. Till next time, goodbye.